under variable amplitude non-proportional multiaxial loading. Okay, so the effective lifetime estimation of the component under real operational complex loading is very complicated task composed from multiple small tasks, and each of them have a critical influence on the accuracy of the estimation. Okay, most of the error that I will be talking about today leads to the conservative results, but nowadays we are trying to design the components to have best ratio between the weight and the bearing forces and so on. So it is important to try to achieve the more accurate results if we can. Okay. So today I will be dealing mostly only with three critical problems during the lifetime estimation under the complex loading, and it will be choosing the correct multiaxial criteria, the way how to incorporate or how to process the non-proportional loading, and of course the variable amplitude loading effects. In this case, it will be only in form of damage accumulation rule. Okay. So about multiaxial criteria, nowadays the most common used criteria, as I can see in the literature and in usage, are the critical plane approach. Of course, there are multiple other criteria, so I will be dealing with three of them, and specifically with Findlay, McDermott, and Matake, and I will be talking a little bit more about it later, and I will explain why I choose these three particularly. Okay, the non-proportional loading is quite or how to incorporate the non-proportionality of loading into the particular lifetime estimation is quite difficult task. In this case, as my main interest will be in the multiaxial criteria and the definition of critical plane, we will be talking about non-proportional loading in the way that I will do the simulation when I load the component with a very simple loading sequence, which is composed from three proportional loading, but each of them have different orientation of principal axis, so the whole sequence acts as non-proportional. Okay, and about the variable amplitude loading, we will use Boundary and minor damage accumulation rule, because I haven't been able to find too much discussion about the influence of this parameter to overall results of particular lifetime estimation under complex loading situation. Okay, so why I choose these three criteria, and what is the main aim of this task? Okay, so in critical plane approach there is again multiple criteria. I heard a joke, I think Mr. Fatem is that everybody have one criteria. So I choose three which are quite popular, and they are well known, but a lot of other criteria use similar approaches. Okay, all three of them are linear criteria which assume amplitude in the critical plane with maximal normal stress acting on the plane during loading cycle, and basically they use different coefficients which scale the normal stresses. But the interesting thing and the interesting difference between them is that while McDermott and Matake criterion define the critical plane as the plane with maximal shear stress amplitude, Findlay criterion define the critical plane as the plane with the maximal damage. Okay. The problem with this definition is that while Matake and McDermott are consistent with observation for example, pure tension loading, when Dr. Professor Polak do some measurement, and lots of other find out that the critical damaging occurs in the plane of maximal shear stress amplitude, Findlay choose this solution. But in the case of non-proportional loading situation, and especially in the situation like we estimate, there are recommendation when you are using McDermott criterion, Matake criterion, you are basically assume the damage in each plane for each cycle, and at the end you are using the approach that Findlay used, so it is inconsistent. At the end, after the loading of multiple non-proportional loading cycle, you are deciding that the critical plane is the plane with maximal total damage, total accumulated damage, which is inconsistent with the definition. Okay, they define for single loading cycle that critical plane is the plane with the maximal shear stress amplitude, for example, McDermott and Matake. But if you use them for non-proportional loading signal with multiple amplitude, you have to calculate damage in each plane, then zoom it and use it. So this can lead to some problems, and I will be talking mostly about this part. Okay, for this presentation or for this paper, we have used the material parameters obtained in our laboratory. I plan to do the example on two material. One is the structural steel S355, and second is structural steel S55 without heat treatment. But if you have a closer look on the fatigue limit for these two, in shear and stress for C55, you will see that it is very, very close. The material without heat treatment acts very strangely, which leads to the very non-standard parameter of Findlay and Matake, and as well to the very non-standard behavior of the criteria, which leads to nonsensical results. So I will be mostly dealing with working with material S355, okay, for this reason. We are doing now some research with C55 and material like this, which have very not standard behavior under the load, torsion and axial loading. Okay. So about the critical, about the damage calculation and non-critical plane. So both Matake and McDermott define the critical plane as the plane with maximal shear orientation. And if you have a look on this diagram, they are basically showing the damage per one loading cycle in the relative way when they are normalized to damage in the critical plane. So the full or solid line is for pure tension loading, and the dashed line is for pure torsional loading. Okay. So if you have a look, you will see that the maximal damage in this case doesn't occur in the so-called critical plane. So if you are calculating the fatigue lifetime for the component which is loaded only with one loading cycle, it is not a problem because you are clearly defined the critical plane. So you are using the criterion in the critical plane, and everything is alright. But if you have the loading sequence which is composed from multiple loading cycle, and each of them is have different orientation of principal axis, you will have to use the different approach. You will have to assume all the damage in each plane, and then you are now assuming the damage from non-critical plane, which is actually higher than the critical plane damage. So it means that your criterion gives you the very conservative results. And the difference between these 2 points is very sensitive on material parameters and the shape of loading signals, which we will see later. Okay, this is the case of C55 steel, and you can see clearly that the inconsistency, the very strange ratio between the fatigue limit in pure torsion and pure tension loading leads to very, very obscure results, and the criteria doesn't work for this kind of steel. Okay, so I won't use them anymore. Okay, for Matake it is not sorry, for Matake it is, yes, for Matake it is a problem. For McDermott it wasn't a problem, but for Findlay it was as well very problematic. Okay, so I will be now dealing mostly in all the picture with the S355 structural steel. Okay, so about non-proportional loading, I do my simulation for 2 very simple tasks. Both of them are composed from multiple loading sequence. Each of these part of the loading sequence is basically proportional loading. So first is the pure tension, second is pure torsion. Okay, the dashed line is torsion loading cycle. The full solid line is a tension loading cycle. The second sequence is composed again from pure tension loading, pure torsion loading, and then proportional tension compression with torsion. Okay. The amplitude of these loadings was chosen that the maximal so-called foam misses amplitude is same for all three of them. Okay, so we will take the maximal normal stress amplitude, maximal shear stress amplitude, and calculate the foam misses stress from them. It will be same for all the three, because it's the problem to design the loading sequence to have similar damaging potential for one loading cycle. Okay. So here are the results for the calculation and what it does. Okay, so this is the first loading sequence composed from pure tension, pure torsion, and the combination. Okay, so red line is the damage per damage in each particular plane for pure tension loading. The blue one is for pure torsion loading, and the yellow one is for is the total damage accumulated using the bulk and minor linear damage accumulation rule. Okay, the first line represents the McDermott criterion. The second line represents the first line represents the Findlay criterion. Second one McDermott, and second one Matake, and third one McDermott. Pardon. Okay, so and the second column is about the signal with three sequences. Okay, so if you have a look on the results, you will see, and it is interesting mainly for this part, that while each of the loading cycle here, for example for McDermott, have a critical plane in different places. So it's it is here, it is here, it is here. The final plane with maximal damage is here. So the damage in non-critical plane in each particular cycle influence the total damage very highly. Okay, so in this case, I assume it leads to very conservative results. This can lead this error, if you can call it error, is very strongly dependent on the material parameters and the shape of loading signals. So we can do a similar simulation with different ratio between normal and shear stresses, and it can lead to very misleading results. Okay, so these are only comparison between the total results. So the blue line is for Findlay, the green line is for Matake, and the red line is for McDermott, and comparison the total fatigue lifetimes for each of them, and the comparison of the orientation of critical planes for the whole loading cycle. So if I conclude the results, I can tell that the multiaxial criteria, which define the critical damage based on some specific condition, like the McDermott and Matake, which define it as the plane with maximal shear stresses, calculate overestimate damage on non-critical plane, which can lead to very conservative results if the component is loaded with the specific non-proportional loading signal or variable to the non-proportional loading signal. The damage calculation on the critical plane is hugely influenced of the material parameters, but as well with the shape of the loading signal. Okay, so if the ratio between the normal and shear stresses. So what are our future goals are to try to find out some kind of correction factor to correctly calculate the damage in non-critical plane. We are doing it now, but we don't have the results from measurements. It's quite difficult to identify specifically which part of the whole process influence the final results. Okay, so that's about it. So thank you very much for your attention.